Let's talk about valence electrons and oxidation numbers. So these are actually kind of the basis for how a lot of bonding works. To start, valence electrons, Val-E, often abbreviated as Val-E there, is the electrons that are furthest away from the nucleus. So for this picture on the left here, you can see that there's some diagrams. You got 1, 2, 3, 4 valence electrons because they're kind of on this outermost shell. Now, we're going to get into those specifics later on in the year, but for now, just know that those are out there. And these are the ones that are responsible for chemical reactivity. Right? So how things react and how things bond, dependent on the element. So elements will have very particular ways that they bond. It's because their atoms have a certain number of valence electrons. Atoms are different elements, so you have different kinds of elements, but if they have similar valence electrons, that means they're also going to behave similarly. So a little bit of information here that'd be nice to know. The number of valence electrons that you can identify in an atom is going to be determined by the group number of its periodic table. So a couple of ways we can know this. One is this group number that's got a group 4A. So just kind of giving you an example, 4A. The 4, right, if you see that as part of its group number, that means it's going to have 4 valence electrons. It's pretty straightforward. Let me show you an example of what that means. So a lot of times on periodic tables, you'll see that numbers on the very top there, those are group numbers, right? So the groups are your columns, and these are how they're numbered. They can be in black, like 1, 2, 3, 4, blah, 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 or in red, you can have it in Roman numerals with 1A, 2A, and then skipping a bunch, 3A, 4A, so on and so forth. So in this example that I just showed, right, 4A, right, IVA, if you have an element in group 4A, it's going to have 4 valence electrons. So carbon, an atom will have, of carbon anyway, will have 4 valence electrons. A silicon, an atom of silicon will have 4 valence electrons, so on and so forth. Alternatively, if an element is in group 2, so that's the numbers just straight across from left to right, it's going to have 2 valence electrons. And then if an element is in group 17, well, it's not going to have 17. It's only going to have 7 valence electrons. Let's see what that looks like. So going back over here, right, this is my group 17. This column right here, they're not going to have 17 valence electrons. They're only going to have 7. How you can know that? Well, one, you also know that the other way that we number this is through VIIA, so 7A, 7 valence electrons. But also, once you start getting into the teens up here, especially from 13 on, if you subtract the 10, you get the number of valence electrons. All right, so kind of putting this into action. How many valence electrons do each of the following elements have? Let's try them out. So we'll start with nitrogen. Nitrogen coming back over here. Nitrogen is right here. Nitrogen, group 15. So if you're going that way, you take 15, subtract 10, you get 5. Or if you look at the alternative here, this is group 5A, right? That's the Roman numeral V, 5A. That's going to have 5 valence electrons. So 5. Potassium, let's find potassium on the very far left here, K, element K. So that's in group 1, group 1A, 1 valence electron, easy enough. All right, go and try the rest of them on your own to see what happens. A new term here, representative group elements. These are elements that are in groups 1 and 2, in groups 13 through 18. These are ones that have very easily determined number of valence electrons, where transition elements, so the ones that are kind of in the middle of your periodic table here, so the ones kind of in this area here, these tend to be a little bit less obvious. Same thing with down here. But the ones here, in group 1s and 2, in groups 3 through 8, these are going to be a little bit more obvious to know. So how exactly do we form ions? Well, remember that there is some reason for it. The reason why ions even form in the first place is because usually the ion ends up being more stable than the regular atom by itself. What exactly is responsible for that? That's a little bit more complicated than we need to get into now. But just know that usually ions are the more stable form of an atom than the neutral one. So when they become ions, what rules do they follow? It's not like they just kind of willy-nilly lose and gain electrons. It actually comes down to the octet rule. Octet meaning 8. Oct, right? As a prefix meaning 8. So when bonding, atoms generally attain 8 valence electrons one way or another. To do so, right, they either can share the electrons with each other or they can exchange electrons, whether it be covalent or ionic bonding. But of course, the key here is that they get 8. So it's going to be kind of one of those things where it just sort of there's some patterns here, but one of the things that's kind of nice is that you can usually expect that, you can predict anyway, are they going to gain or are they going to lose electrons to satisfy the octet rule? Well, let's try this out. Let's try sulfur, right? Sulfur. So sulfur, if you look at the periodic table, which we'll look at right now, sulfur is right here. Sulfur is in group 6A. So being in group 6A, that means it has 6 valence electrons. So if you want to attain the octet rule, all you have to do is gain 2. So sulfur is actually going to gain 2 electrons in order to achieve the octet rule. What about rubidium? Rubidium, over here, right on the very far left, RB, it's got 1 valence electron. So that's going to have, to kind of decide on now, well, we can gain 7 electrons, right? That's possible, but not that you necessarily know this immediately. There's kind of a little trick to this where if I actually lose 1 electron, that actually will help me attain the octet. So there's kind of like an underneath octet. If you were to lose it, that's how it gains the octet. Kind of counterintuitive, especially when the language suggests you want to get to 8. 0, what seems like 0, losing an electron does not seem like you're getting to 8, but that's kind of an understood there. So kind of assume that when you have lower numbers of electrons, they're going to lose, higher numbers are going to gain. Let's try chlorine now. Chlorine. Next one right here, chlorine Cl over here. It's in group 17 or group 7A, so that's going to have 7 valence electrons. That means you're going to gain 1 electron to attain the octet rule. Nitrogen, if you go back and look at the previous examples, or if you just kind of peek at the periodic table again, you'll find that it has 5 valence electrons, so it's going to gain 3 electrons. Now, as a result, what will be the charge of the ion once those atoms of the element lose or gain those electrons? So sulfur, when it becomes ion, will have a charge of -2. So I'll have an ion charge of -2. Rubidium will have a charge of +1. Chlorine will have a charge of gaining 1 electron, -1. Nitrogen, because it gains 3 electrons, will have a charge of then -3. This is a kind of an outline of the periodic table, and this is kind of a nice little pattern that we can use. So one of the things that's included on the periodic table, or oftentimes anyway excluded, but you should be able to mentally include it, is that usually there's kind of like this sort of imaginary or sometimes drawn out zigzag line starting up here where this element would be. This actually ends up being boron, and you kind of zigzag it all the way down. What this does is that kind of conveniently separates the periodic table into metals, metalloids, and non-metals. So kind of in this section over here to the left, all right, so all this, and we'll kind of lump that into, and mostly some of these are your metals. These will typically lose electrons. Whereas over here on the right, this in green, all these, again, tend to be your non-metals. That's where these non-metal elements tend to be located on the periodic table. These will typically gain electrons. So usually just by identifying it as a metal or a non-metal, you can kind of predict whether or not it's going to gain or lose electrons. Kind of in this sort of no man's land in between, I'll go ahead and talk about this. These are typically your metalloids, and these elements, it's not really one way or the other. Sometimes they gain, sometimes they lose. It's not very obvious sometimes, so we're not going to make any conclusion about those. Thankfully, most of the examples, or all the examples we really work with, are going to come from the metal side or the non-metal side, so you can very easily predict if it's going to lose electrons or gain electrons, because as it kind of makes sense, right? If you are over here, that means you have more electrons. So you're closer to 8. Say you have like 5, 6, or 7 valence electrons. So to attain the octet rule, you're just going to gain electrons. Whereas over here, you might only have maybe 1 or 2 valence electrons. And someone here is kind of is different. We'll talk about that later on. But right here in the middle, or on the very far left, it only has 1 or 2 valence electrons. Those are likely to lose it to attain the octet rule. So there's actually specific terms other than just calling it gaining and losing. Is something we call reduction and oxidation. Reduction is a process by which an atom gains electrons. Oxidation is a process by which an atom loses electrons. So this is going to be one of those things where you kind of basically expect that these are opposite processes. So magnesium is an element that will end up being 2 valence electrons. That's terribly writing. So try that again, 2 valence electrons. So these 2 valence electrons, right, because we typically expect things with low numbers of valence electrons, we expect them to lose it. So we're going to write it as if it loses it. We're going to write a little equation here. Let's start with magnesium. Magnesium is going to lose electrons. So what's going to happen is that you're going to write it where it loses 2 electrons as part of an equation. These 2 electrons kind of go away. And then to finish out the equation, we're going to know that magnesium, because it lost those 2 electrons, now becomes a +2 ion. This is an example of oxidation, right? So oxidation is where we're losing electrons, so it lost 2 electrons, so it becomes magnesium 2+. Bromine has 7 valence electrons. Bromine with 7 valence electrons will probably want to gain 1 electron. So by gaining the 1 electron, it becomes, some charge. So let's see how this works out. Bromine, Br, we're going to write it in the equation where Br plus the electron, again, because it's being added, not because it's being lost. It becomes, as an added substance, we then form something new, like Br, with a -1 charge. All right, it's going to gain 1 electron to attain its octet rule. Over here on the right, you kind of see some pictures. You've got a couple of things you can take away from this. First of all, we can call this oil rig to represent oxygen is losing, reduction is gaining. And of course, when they talk about losing or gaining, they don't explicitly say that here, but we're talking about electrons. Oxidation is losing electrons. Reduction is gaining electrons. Oil rig. Down here, we can also have an alternative, Leo Grr, right? Because Leo the lion, typically that's the kind of name we associate with lion. Losing electrons is oxidation. Gaining electrons is reduction. Of course, this is definitely not a lion. It's a tiger, but it's a mistake I made years ago. I don't feel like changing it, so there it is. Moving on, redox practice. So what process will each of these elements undergo to become stable? And let's see what we have to write to make that happen. So with cesium, right, looking at the periodic table, cesium is going to be on the very far left right here. Cesium is an element in the 1A. So no, offhand, cesium is going to have one valence electron. With one valence electron, we typically expect it to lose the electron to attain the octet. So we know then it's going to undergo oxidation. And then, as a result, right, we can, with this information, write an equation that represents that. So cesium, symbol is Cs. It's going to lose the electrons, so we're going to write the electron as something that is produced from this process. It's lost by this cesium. And then, as a result, the remainder, right, whatever's left over, is now going to be Cs plus, and it lost a negative electron. And the sulfur is going to have 6 valence electrons. You have to be able to gain 2 more, so to reach the octet. So by gaining 2, that's going to undergo the process of reduction. So then sulfur will gain 2 electrons, and then inherently becomes S2 minus. Right? So we'll gain those 2 electrons embedded within the atom, and so we simply represent it as an ion, S2 minus. So as you can see there, we kind of had a bit of a predictive ability to say, hey, these atoms or these elements are going to gain or lose a certain number of electrons. And that's what oxidation states basically are. So when a neutral atom becomes an ion, it adopts a very predictable charge. These charges are predictable charges, and we just collectively call them oxidation state, or we call them oxidation number. Now, technically, they're not exactly the same, but for all intents and purposes, what we're going to do here, they're going to be considered the same. It's very much related to the number of valence electrons, right? Because the number of valence electrons helps us inform us, anyway, know when we gain or lose a certain number of electrons, and when they gain or lose, it's going to adopt a certain charge. By the way, atoms that have not been altered, right? So if you have neutral atoms, regular atoms that are not part of a bond or haven't been switched around, those are going to have an oxidation of just 0. Okay, so some patterns here. Let's go and see what happens. So group 1, group 2, and group 13. Those typically will have oxidation states when they gain or lose electrons. In this case, they lose them of +1, +2, +3. So group 1, group 2, and group 3, right? Those are going to refer to these 3. So those elements, when they undergo, again, I'm not saying that these elements, when they're pure, adopt a charge, but when they undergo the change, in this case, oxidation, they adopt a charge of +1, +2, +3. As opposed to our friend here on the right side, right, coming from the right side, so group 18, 17, 16, 15, so kind of going 18, 17, 16, and then 15, those become 0, -1, -2, -3. So kind of coming from the left this way, or sorry, coming in from the right this way, it goes more and more negative, whereas coming from this way, it becomes more and more positive. This is worth memorizing, right? Because while you can walk through every single time how many electrons it has, or how many valence electrons it has, how many it's going to gain or lose, it gets a little tiresome. So just go ahead and throw them in there. A couple more notes on oxidation states. Transition metals, those are the metals that are kind of in the middle section. So as I mentioned earlier, this kind of area right here, and all these elements right here, those tend to have a less obvious pattern, so we'll talk about those later on. Metals will all typically have positive oxidation states. Non-metals will typically have negative oxidation states, basically repeating what we saw before, predicting what the charges are going to be. And of course, as a reminder, this oxidation number, oxidation state, and the word charge, that also kind of has interchangeable meanings here. All right, so for this, let's go ahead and give you a chance to practice this on your own. For each element, I'm going to ask you to determine the number of valence electrons in that atom, whether or not it's going to undergo oxidation or reduction, the number of oxidations or number of electrons that it undergoes, or electrons that it's either lost or gained because of this process, the resulting oxidation state, and then finally the equation for the reduction or oxidation that's expected. And I tried to write a couple more of those out earlier to give you a sense of what that might look like, so hopefully that will give you a good background for this. One last thought, though, is worth mentioning. So notice how, again, the word oxidation state's being used here. So even if something undergoes reduction, that actually kind of is ignored once you designate an oxidation state. Somehow, some way, some scientists a long time ago decided that's the term we're going to use, even though something might undergo reduction. The resulting charge we still just call the oxidation state. All right, that'll do it.